it is a section 4.2, row reduction and the general solution of linear systems. In the last section, section 4.1, we studied 3 elementary row portions. In this example, we'll try to find the solution of the given system using the 3 elementary row portions. Okay, here we may begin with the augmented matrix. So let's try to collect the coefficients 0, 1, minus 2, 0, 1, minus 2, and 1, minus 2 and 2, 4, minus 8 and 6, and the right side 0, 3, 14. This is the augmented matrix. Okay, this value is 0, so we may interchange first and the second rows, 1, minus 2, 2, and 3. Okay, and here 0, 1, minus 2 and 0. And now for this last one, okay, let's try to subtract 4 times of this row from here. Then there will be 0, 0. 4 times subtraction minus 2. 4 times subtraction, that is 2. Okay. Now, okay, this last row can be scaled. Okay, we write down here, divide by minus 2, so that can be 0, 0, 1, minus 1, right? Okay, so rather than this one, we may consider this row. Okay, now here, this is the leading one, another leading one, another leading one. So here we have to eliminate in this these 2 values and also these values. Let's try to eliminate these 2 values first. Okay, that is, okay, twice subtraction. Just 1, minus 2, and 0. Twice subtraction, that becomes 5. And then twice addition, 0, 1, 0, and twice addition, minus 2. And here the last row is 0, 0, 1, minus 1. Now, using this one, we can eliminate that value. Twice addition. Then here, there's 1, 0, 0. Twice addition, so it is 1. Now 0, 1, 0, minus 2, 0, 0, 1, minus 1. So it becomes the identity matrix, and so that this one is the solution. 1, minus 2, minus 1. It is the unique solution. So the system is consistent, right? The system of linear equations can be solved by transforming the augmented matrix to the reduced row echelon form. That is, the reduced row echelon form will define the term very soon. In MathTalent, we have a function RREF for the reduced row echelon form. Here A is defined in the same way, this portion, and B is now this right side, and we got augmented matrix AB, and we try to find the reduced row echelon form. Now the result is given in this way. So we can find the solution, the last column. Okay. Here we define echelon forms and consider the row reduction algorithm. A rectangular matrix is in an echelon form if it has following properties. Okay, all non-zero rows are above the above any zero rows. A row has non-zero entry, then that must be above any zero rows. That means that rows of all zeros should go down. By using interchange, you can do it. The leading entry, okay, a non-zero row is given, then first non-zero from left-hand side is called the leading entry. Each leading entry in a row is in a column to the right of leading entry of the row above it, which means that here leading entry is now down and right direction. So, okay, let's try to make a figure here. A matrix is given, and then we can apply elementary row operations so that we can make later here. The shape is given in this way, like that. Here, there's a leading entry, and reading entry. Zero rows will be on the bottom, like that, and below leading entry is 0. So the below the leading entry in a column is zeros. So once it is made in this form, then it is called an echelon form. Echelon, by definition, is a shape of a ladder, and one side is narrow and gradually becomes wider, like here, so that here, and this shape is echelon form. Okay. Now, if two extra conditions here are satisfied, then it is called row reduced echelon form, or simply reduced echelon form. The leading entry, leading non-zero entry in each non-zero row is 1. So that by scaling, if you make, you can make this leading entry become 1. And again, the leading one is the only non-zero entry in its column. So after changing this leading one, and below and above, every other entry must be 0. Then these two extra conditions are satisfied. Then an echelon form becomes the reduced echelon form. Let's see here examples in this. Okay, example 4.13. Okay, here. Now this is a leading entry, the leading one. Leading entry, that's 1. And so it has an echelon form, and 0 row is on the bottom. This is echelon form. Also, the leading entry is 1. It's satisfying the condition 4. How about condition 5? This leading one is only the non-zero entry in its column, so that here we have zeros and zeros, so that these extra two conditions are satisfied, so that it is the reduced echelon form. Okay. Now how about this one? That is a leading entry, leading entry, leading entry. Okay. So it is not in an echelon form. If you interchange these two rows, then it is in an echelon form. How about this one? This is a leading entry, leading entry. They are ones, and except these leading ones and the columns here, other values are 0. So it is a reduced echelon form. Okay. Let's see this one. This is a leading entry, leading entry. Okay, leading entry is down and right. So it is in an echelon form. However, the leading entry is not 1 here. And also, these are not zeros, so that it's not in not the reduced echelon form, but it's in an echelon form. Okay, so that is echelon form. Okay, now here leading entry, leading entry, leading entry. So it is in an echelon form. However, now these are non-zeros, so that it's not reduced echelon form. It's only echelon form. Okay. How about this one? Is leading entry, leading entry, leading entry. So it's not in an echelon form. Okay. However, if you interchange these two, then it is in an echelon form, but not yet reduced echelon form. Okay. A pivot position is a location in the matrix A. So you have to find the location in A in the matrix. Okay. That corresponds to the leading one in the reduced echelon form of A. Okay, let's see this example. For this given matrix, we have reduced echelon form. Here, leading one, again leading one. Okay. Now, so here the position in A, corresponding position, is called pivot position. So here, this one and that one are pivot positions. A pivot column is a column of A that contains a pivot position. So that if we call A1, A2, A3, A4, A5, then A1, so therefore this example, pivot columns are A1 and A3 and here A5, right? 3 columns are pivot columns for this one. Now, here, these two are called non-pivot columns. Okay. We continue the terminologies. The basic variables. In the system AX equals B, the variables that correspond to pivot columns in the augmented matrix are basic variables. So once we try to use this matrix, for example, and we try to solve AX equal B, then, and after elementary row operations, we can reach this one and here some vector. Okay, here we found here, we can see, and first column, third column, fifth columns are pivot columns, so that here x1, so corresponding variables are just x1 from here, and x3 and x5. These three are basic variables, and now non-basic variables, which is called free variables. So x2 and x4 are free variables. We'll see why it is called, why they are called free variables. Here in the system AX equals B, the variables that correspond to non-pivot columns are free variables. That means that once it's not a basic variable, then it is a free variable. Okay? Okay, let's see this example. For the system of linear equations, identify its basic variables and free variables. So here, that is, we have to work on the augmented matrix and try to find the pivot positions. And then the corresponding variables are basic variables and others are free variables. Right? Okay, so let's begin with the augmented matrix. Okay, for the system, so -1, -2, and the third one is 0. And for the matrix, 0, 0, 2, and 0, 0, 3. These are the coefficients, and this whole thing is the coefficients matrix. And right hand side, -3, 4, and 6. Right? Okay, that is the augmented matrix. Okay. Now here we apply scaling, divide by 2, divide by 3. Then also we multiply -1. Then that is 1, 2, 0, and 3. This is 0, 0, 1, 2, 0, 0, again 1, 2. Okay. So that here we can eliminate the bottom row. Okay. Let's rewrite here 1, 2, 0, 3, 0, 0, 1, 2, 0, 0, 0, 0. Okay. Now, okay, so here we found here this is in this reduced echelon form of A. This is leading one and this is leading one, so that we already know that basic variables are x1 and now x3, the corresponding variables to the pivot columns, and free variable, that is x2. Okay, here we have x2 as a free variable. Let's see why it is called a free. Okay, the system here is the same as this one. The first row is same as x1 plus 2x2 equal 3, and that is x3 equal 2. The second one, that is same as x3 is 2. Now, from this one, let's try to find the solution, but we have to find the values for x1, x2, x3, all of the variables. For all of the variables, you have to find the values. That will become solutions. Okay, so now to solve these equations for x1, x2, x3, we keep basic variables left hand side, everything else to the right side. Okay, so x1 equal 3 minus 2 x2. Now also we have to find a value for x2. So we write down here, but there's no equation for that one. So we may write down x2 is x2. It's always true, so it's okay. Now how about x3? That is now 2. Then for this vector x1, x2, x3, we can write this right side in this way. That is a 3, 0, 2, a vector plus x2 and minus 2, 1, and 0. The coefficients are minus 2, 1, and that is same as 0, x2, right? So we can write in this way. Okay. So here, for the solution x1, x2, x3, now this vector plus x2 times minus 2, 1, and 0. In this solution, x2 can be chosen arbitrarily. You can choose x2 freely. And for any choice of x2, the result will become a solution. So that's the reason x2 is called a free variable, because you can choose freely. Okay. Now here is the row reduction algorithm, and I'll try to explain the algorithm through this example. Row reduce the matrix into the reduced echelon form. A is given here. Now that this value is 0, so we apply interchange, okay, along with the third row. So it is 1, so it is easy to handle later on. So after interchange, we have that one. Now, this is pivot, and we have to eliminate the below the pivot. So multiply 2 for the first row and add to second row. That's the operation to make it 0. Then this position becomes a 5, and we're done for this pivot. Now we move our attention to this value, and now to make it handle easier, we divide by 5. So we have here, and 3 times can be added to make this portion 0 below the leading entry. So here we make this one 0. Now we recheck this metric so that this becomes a pivot. Now divide by -5, we have this one. So that these are pivot positions and all values are 1. Here, now to reach at the reduced echelon form, we have to eliminate above the leading ones. So these two values and this value. We start with this one. So first -9 and -3 will be eliminated by adding 9 times of this one and by adding 3 times this last row. Okay, then we reach that one. Now we can eliminate that one. So here 4 times of this row will be subtracted from the first row, and we can make this one 0. So we reach this reduced echelon form. Here leading ones on the columns, except leading ones, every other values are 0. Okay, so it is the reduced echelon form. Now, when we try to eliminate these two values and that one, okay, we can eliminate, okay, here, this one and that one. If you try to eliminate this one first, then after elimination of that one, if you try to eliminate this one, then it's okay for this shape, and after elimination of that one, now you can do it again here, and you can eliminate this one. However, in this case, it will be more expensive. Once you eliminate this portion, then it will become 0, so that later on, when you eliminate this value, you don't have to worry about this position. So usually, elimination of the values above the pivot value is backward way is happening. Right? Okay. Okay. Now let's see here the combination of operations in line F. Here, this F and F is the fourth phase of row deduction. So first we try to, using this pivot, we try to eliminate this one. And by using this pivot, we try to eliminate this one. And then here, now we reach this echelon form. So through this fourth phase, and now down and right direction, we try to eliminate, and we reach this one. That is echelon form. This phase is called the fourth phase. And from here, we try to eliminate above the leading one. And we eliminate here, and the backward way, eliminate this one, and then now eliminate this one, so that in backward way, we try to eliminate the values. So this the combination is called the backward phase. Okay, so through forward we reach at echelon form, and through backward phase we can reach at the reduced echelon form. Okay. Pivot positions. Once the matrix is in an echelon form, further row operations do not change the positions of the leading entries. Thus, the leading entries become the leading ones in the reduced echelon form. Okay. In definition, here pivot position is the location in A that correspond to the leading one in the reduced echelon form of A. So pivot position is decided by the leading one in the reduced echelon form. However, in reality, once you reach at an echelon form, then these leading entries is not changing the position in the further operations. Okay, these leading entries are changed into here leading ones, and it becomes the reduced echelon form. However, the positions are not changed. So that once you reach at echelon form, then here you can decide pivot positions. Of course, pivot position is in the matrix A, and also pivot columns are, in this case, 1 to 4th. The columns, these are pivot columns, not in this echelon form. Okay. Here, each matrix is row equivalent to one and only one reduced echelon form. This means that, and here, for this given matrix, this is an echelon form. Also, after scaling, this is also an echelon form. Also, this one is an echelon form. They are not at reduced echelon form. However, these are echelon forms. So echelon forms are not unique. So you can have various echelon forms. If you want, you can get infinitely many echelon forms for a given matrix. However, if you try to get reduced echelon form, then reduced echelon forms are unique. You can have only one and one reduced echelon form, so that one and only one reduced echelon form exists for a given matrix. So this is the unique reduced echelon form of the given matrix A. Okay. Okay, we'll continue in the second part. Thank you.